So we're not going to go over the quiz per se, but lots of what we do will kind of let you know. Okay, can we stop talking, please, so we can get started and get everything done today? Ready to start. Here we go. Okay, that means stop talking. I gave you the minute to wind down. So now it's time to stop talking all together. Okay, so here is this rate of change function g. And so now I'm giving you a couple points. Those weren't not on the quiz. So what is the approximate rate of change at x equals 1 according to this linear piece that's pretending to be g? Go, find it. So what is the approximate rate of change at x equals 1 according to this linear piece pretending to be g? Be a piece of cake. What'd you get? I heard lots of negative 2/3. And this is for h equals 3. At x equals 1, h equals 3, you get negative 2/3. Okay, so what we really want, though, is we want a much better estimate. A much better estimate of this value of rate of change at x equals 1. How can I get a much better estimate? Make h really small, right? So let's zoom in here. We'll zoom in, and we'll take h of 0.05, and I'll give you the point there. So now we got 1, 4, and h of 0.05. And when you do that same process that you just did, you get a rate of change of negative 1.3. So clearly, this negative 1.3 number is going to be a lot closer to the true rate of change at 1 than the negative 2/3 was. Okay, similarly, we could look at down here at 4. We can do another example. Same h, 0.05. And we want to know, we're trying to find, or estimating the rate of change at 4. So what would that process look like to estimate the rate of change at 4? Our numerator would be, what would our numerator be? Well, so 1.983 minus 2 divided by 4.05 over minus 4, or that's h, 0.05. And when you do that, you get negative 0.330. Okay, again, so this may be the most important question all semester. What do these rate of change values mean? Negative 1.311, negative 0.33. Take a minute, talk to the person next to you. It's probably one of the most important questions all semester, that you know there's so much packed into these numbers. There's so much important, such an important idea, and a complex idea, packed into these numbers. And you need to know what those numbers mean. So talk to the person next to you. Go. Okay. So here's one possible way to interpret them. And it's been the way we've been really focusing on a lot lately. You could say that at 1, for a small change in x, the corresponding change in y would be negative 1.311 times as much as that change in x. How many people said something like that? Oh, not enough. Okay. So again, I'll say it again. Near 1, for a small change in x, it could be 0.01, could be 0.001, could be any small change in x around 1, that corresponding change in y will be negative 1.311 times as much as that change in x. Okay? Similarly for 4, if you take a small change in x close to 4, your change in y will be negative 0.33 or about negative a third as much as the change in x that you picked. Okay, so that's what we've been emphasizing on. But there's another, way back at the beginning of the semester when we were doing all this stuff about constant rate of change, we had a kind of a slightly different meaning, and I want to talk about that. So these numbers were found by a quotient, right? A quotient, delta y over delta x. Who remembers what a quotient represents? Okay, say, yeah.
So one in size relative to the size of another.
So in this case, the size of what relative to what?
Delta y to the size relative size of delta x.
Right. So it's the size of delta y relative to delta x. Remember all those bar diagrams we did to try to understand what a quotient means. Okay. So another way to look at this is to say that these numbers are the relative size of the change in y to the change in x. The relative size, change in y, to the change in x. So if we try to erase all this, give me some room here. Come on. Where are you? Okay, so basically what we're saying is here's our change in x, corresponding change in y. And how does that change in y relate to the change in x? Negative 1.311 times that change in x. So this decrease in y is negative 1.311 relative to that change in x that we picked. And so then, down here, similarly, now I pick a change in x here. What about the change in y now? Right, so only a third of the decrease, right? So a decrease of a third of what I picked for delta x. So if x and y represented two quantities, what can you say about how they're changing together? So around x equals 1, how is y changing relative to x? Around x equals 4, how is y changing relative to x? This is what it's all about, right? So this is what this number rate of change means. As x is changing, y is changing negative 1.3 times as fast as x is changing. But then when we get to x equals 4, now how is y changing? Totally different, right? It's only going down a third as much as a change in x. Whereas before it was going down more than the change in x. Okay? So what we have is a changing rate of change. Changing rate of change, and that rate of change is the relative size of a change in y to a change in x. Or how fast y is changing in relation to x changing. So these numbers, these rate of change numbers are loaded, okay? They're loaded. There's a complicated idea behind a single number, okay? And then now you have a changing rate function. So at every x value, you have a different rate, okay? And so understanding those numbers is crucial. That's why I've been working so hard on it. Anybody have a question? Okay, so here is that g function. So it could have been the function on your quiz because you had no numbers. So now we want to find the closed form. Another thing we've been working on lately is finding a closed form for the rate of change function, meaning a function, instead of having to pick 2 points that are really close together and calculate delta y over delta x to get the rate of change, Could we find a function that all we have to do is plug in 1, and it just tells us what that rate of change is? That negative 1.311. Okay, how do we do that? What's our first step? What is r of g of x? It's the change in y for a change in x of h over the change in x. Our rate of change function. It's our approximate rate of change for a change in x of h. Okay, so now we've got the function now, we can apply it. So what's g of x plus h? That means the input is x plus h, so this function will be 12 over the input plus 2. That's what this function says. It says take 12 over the input plus 2. Our input is x plus h, so we take 12 over the input plus 2. Minus g of x. That thing all over h. Oh, x plus 2, sorry. X plus 2. Are we good? Okay, so we can't do anything with the denominator. H is just h. So we got to do something with the numerator. So we got to subtract these fractions. That means to subtract fractions we need common denominator. All right, so here we go. So it's just going to be the common denominator will be the product of the two denominators. There's no common factors to those, so we got to multiply them together. That's our common denominator. So making the common denominator here will be multiplying by x plus 2, so it'll be 12 times x plus 2 all over x plus h plus 2 times x plus 2 minus 12 over x plus 2. This one's times x plus h plus 2, top and bottom. And that whole thing is, all right, how did I do? We get it right? I don't want to waste too much vertical space here. Can we write it that way? So can we do two steps at once here? I want to actually subtract and then simplify the numerator. So on the numerator, I'm going to get 12 times x plus 2 minus 12 times x plus h plus 2. So really all we'll have left in the numerator is just negative 12h. Do you see that? Because you have a positive 12x plus 2, and then you have a minus 12x plus 2. So all you'll have left is from that second fraction, the negative 12h. Can you see that? We need the time, so that's what I'm going to do. All you have to do if you're not sure is just, after class, just work out the intermediate step, and you'll see that this is what this is. And then it's times x plus h plus 2 times x plus 2, all divided by h. Okay, what do you see now? We've got a negative 12h and then that whole thing over h. So h over h now is 1. So I got negative 12 over x plus h plus 2, x plus 2. Any questions? We're not done, not quite done, but that's as simplified as we can get for the rate of change of g with respect to x for some h, some finite h, right? Anybody have a question? We good? So is that approximate or exact rate of change function? Approximate, okay? But it could be exact if let h be very, very small, so it's indistinguishable from what you would have if h was 0, right? So like h gets so small that you just can't, there's no distinction between that number and when h would be 0. So therefore it equals negative 12 over x plus 2 squared. sorry. Okay, so we just found on the previous page, we looked at small change in h, we looked at a very small h for two different values, and we got that r of g of 1 was negative 1.311, and rg of rate of change of g at 4 was negative 0.33. So let's see how we did with this closed form function. So what can we do to check this? Okay, the rate of change of g with respect to x when x equals 1 is going to be then negative 12 over 9, right? No, is that right? Yeah. What is that? Or negative 4/3, which is negative 1.333. Pretty dang close to what we calculated. What about r sub g of 4? It's going to be negative 12 over, so 4/36, negative 1/3. So the importance of the previous screen is really understanding what the numbers mean, right? It's the relative size of the change in y, the change in x. The importance of this screen is how powerful a closed form rate of change function is. All we have to do is just stick 1 into that function, and it just gives us the rate of change, the exact rate of change at x equals 1. Stick 4 in. So we can get rapid fire rates, as many as we want, really fast. So that's what's so important about having a closed form rate of change function. Maybe more important, well, as important is understanding what these numbers mean. That was what the previous screen was for. Okay? Any questions on that derivation? So just in your web work, they call this, just while I'm thinking of it, they call this the difference quotient, right? Because it's two differences in a quotient. We know that's the constant rate of change from x to x plus h, okay, of our function g. But just know that they call that the difference quotient. Any questions on this page? Okay, so given any exact accumulation function, g of x, like we just had, its exact rate of change function is called the derivative of g. It's called the derivative. So, in our example, negative 12 over x plus 2 squared is the exact rate of change function for the function g of x equals 12 over x plus 2. That's what we just found by doing the math to find the closed form. Okay? And thus, negative 12 over x plus 2 squared is the derivative of g. The derivative of g. Okay, so notation for the derivative. So derivative specifically is now, it has to be the exact rate of change. The exact rate of change function is what is called the derivative. So for notation, here are two notations that are most common. This one here, that means the derivative. This one here, this means the derivative of g with respect to x. And so if it's the exact rate of change function, we know they both have to equal this. The limit as h approaches 0 of our constant approximating rate function. Okay, so what about r of g of x? Does it mean the derivative? This notation, r g x, does it mean the derivative? Maybe. If h is extremely small, it does. Okay? If h is extremely small. So this is kind of our generic notation to mean the approximate rate function, the approximate rate of change function for g. But it's versatile because if h is very small, it is the derivative. Okay? But all of them, all of those, whether it's our rate of change function r or the derivative, they're all read as the rate of change of g with respect to x. Okay? So we're going to practice that as much as we can, because that's what it is. The rate of change of g with respect to x. So even though it is the derivative, and we say, and so this could be said g prime, we're going to avoid that as much as we can and keep practicing. The idea is it's the rate of change of g, or the exact rate of change of g with respect to x. Any questions? Okay, so rules for finding closed form derivatives. So we've seen how powerful it is to have a closed form derivative like the one we just had. All we had to do is plug 1 in, and it gave us that rate of change. Plug 4 in, gives us the rate of change almost instantly. So we're going to develop rules for finding closed form derivatives. Your mastery test is about your knowledge and ability to apply these rules. Okay? So here are the first 4. So we did one on Friday. Recall that if f of x was x to the n, the exact rate of change function was n x to the n minus 1. Okay, so we could say this now. So the rate of change of f with respect to x is n x to the n minus 1. So that's our first rule that we talked about. Okay, and we'll call this the power rule. The power rule. Okay, when you have x, your input to a power, its rate of change function is that power times x to the n minus 1, or 1 less than the power you had before. Okay, so the next rule we'll talk about is constant functions. Okay, so an accumulation function f never accumulates any changes in its value, meaning that no matter what its input is, you get a constant. You get a constant value. What about the rate of change? It's constant, so the accumulation is constant. How fast is it changing? 0, it's not changing, right? It's not changing. Okay, so how does that work out? So this is the class of functions where it's just a constant. No matter what input you have, you get that same value. And so as a graph, you know that so no matter what x you get, you just have the same y value, right? Constant function. So in order to find a rate of change function, we will always start with this. Okay, so in your web work, you've got some of these. We're going to do some more of these, but anytime you want to derive a general rule or a specific closed form rate of change function, we always start with our rate of change function in open form. Okay, in open form. So what is f of x plus h? No matter what the input is, it's c. So what's f of x? C. So you get c minus c over h. And that's 0. So that's showing it, proving it mathematically. Okay, so the rate of change of f with respect to x, if f is constant, is 0 because it's not changing. So the rate of change is 0. Okay, next, so we got 2 rules now. We got 2 rules. Here's another one, constant multiple. So we're to kind of build the idea of the constant multiple, we'll start with an example. Okay, so this is an example. At every moment in time, John has traveled 5 times as far as Mary. What can we conclude about John's speed relative to Mary's speed? So his distance is always 5 times as much as Mary's distance. What about John's speed relative to Mary's speed? Would you buy this? That his speed is 5 times as much as Mary's speed. If his distance is accumulating 5 times as fast as her distance, that means his speed is 5 times as fast as hers. So if f was John's total distance after x hours and g was Mary's total distance after x hours, then here's the given situation that the distance John travels is 5 times as far as what Mary travels, and our conclusion was that he must be traveling 5 times as fast as her. his rate is 5 times her rate. And that should just make sense. This should be common sense. That shouldn't feel like a stretch. Okay, so then we could say that this is using these other notations to mean the same thing. Using these other notations to mean the exact same thing, but again, all of them we read as the rate of change of f with respect to x is 5 times the rate of change of g with respect to x. All those things mean that. Okay, so this was more of an example of constant multiple with distance and speed and time, but the constant multiple principle applies to any functions. So that would look like this. Okay, in any value of x, function f has a value that's c times as large as the value of g. Therefore, the rate of change of f is c times the rate of change of g. Okay, that's now just the general version of the constant multiple rule. And then again, so here would be your notation showing that. Again, they're all read as the rate of change of f with respect to x is c times the rate of change of g with respect to x. So Friday's recitation and then recitation this week, Monday and Wednesday, you're actually going to be algebraically deriving these rules and proving that they're true. Okay? So we're not going to take time in lecture to do it. You're going to do it in recitation. So that's rule number 3. We got the power rule, we got the constant function rule, and now we have constant multiple. That if one function is a constant multiple of another, then its rate of change function is that same constant multiple of the rate of change function of the first. Okay, last rule for today. And then we'll put them all together and practice the problem. So, if you have a function, say k, that's the sum of other functions, what would you hope for? That the rate of change of k would be? The sum of the rates of change. And it's your lucky day. The rate of change of k is the rate of change of f plus the rate of change of g. So this is one way to say it. Here's another way to say it. So you could say the rate of change of f plus g with respect to x. Here's one of our derivative notations. But these are all saying the same thing, just with different notation. Here's the other derivative notation. What's that? Hess's law. I don't know what Hess's law is. Maybe. Maybe. I don't know. Never heard of it. Okay. Again, so these notations, these second ones would be for exact rate of change. Exact rate of change. We know this generically is approximate, but could be exact if knowing that if h is very, very small. Okay, so summary. First one. So these are the 4 we've talked about. If you have the power rule, then the rate of change function is n x to the n minus 1. Constant function, the rate of change of a constant function is 0. Constant multiple, the rate of change is that constant multiple times the rate of change of that function. And then if a function is the sum of functions, its rate of change is the sum of those rate of change functions. So here's an example that has all of those rules involved. So let's look at where do we see x to the n? Where do we see that? Okay, right there. So if we were going to write the rate of change of p with respect to x, what's up? Is there a question or really like this example or? Okay. All right. So, what's the rate of change of x to the 11th? Oh, first of all, the first thing is, what's the overall structure of this? The overall structure. Is it 1, 2, 3, or 4? 4. The overall structure is we have sum of many functions. So the first thing we look at is we say, oh, it's going to be the rate of change of the first one minus the rate of change of the second one, plus the rate of change of the third, plus the rate of change of the fourth. So that's the first thing we do is look at the overall structure, and we would be applying that fourth rule. Okay, then the next thing we would do is come to this one, and we'd apply which one? 1, 2, 3, or 4? 1. And it would be, the rate of change would be 11x to the 10th, applying rule number 1. Okay, then we come to this. What rule do we apply to this first? We have negative 5 times a function. 3. The rate of change will be negative 5 times the rate of change of that function. This is rule 3, which is 4x to the third. Which rule do we apply first here? Third again. So it'll be 10 times the rate of change of x cubed. Which rule do we apply here? Number 2. Rate of change is? So that polynomial uses all 4 of the rules somewhere. Anybody have a question? Okay, cards.